So I'm going to talk to you today about transiting exoplanets. Probably Andres have told some of you what this is about, but I'm still going to assume no one knows anything about this topic here. And what about the detection of these new exoplanets in the era of new space-based technology? So the main idea behind this discovery and characterization of exoplanets is to try to understand the diversity of worlds out there, right? So we most likely are familiar with the planets in our own solar system, and we also might wonder if this natural feeling that we have regarding our solar system also applies to other planetary systems out there. So this can actually help us understand, how planets are formed, what are they made of, how common my favorite element is, our favorite element most likely is water. And then you don't have to look actually far away. You don't actually have to go to other planetary systems to start answering some of these questions. So for example, if you look at the solar system, in the solar system, you can already see some hints of what planet formation looks a little bit. So this is a very nice plot that I love from a paper in 2016, in which you can see here in the y-axis, what is the abundance of different elements in the x-axis in different planets with respect to the abundance of that same element in the sun. So if the planets, for example, as some people believed like hundreds of years ago, or no, not so much, but some years ago, if you believed that planets form from exactly the same materials as the sun, in the same stars, then all the planets, all the compositions should lie in this one line here, but they do not. So for example, Jupiter is about 2 to 3, 4 times more enriched in all the elements than the sun. So this is here Jupiter. Saturn is about 10 times, and then Uranus and Neptune, it's around 100. As you can see, there's some hints here that something special is happening in planet formation. And actually, this was quite understood some years ago. So we're speaking of 20, even 30 years ago, with the core accretion scenario. So the core accretion scenario basically posits that you start, when you form these giant planets, you start with what we call these seeds of metal-rich material. So whenever an astronomer speaks of metals, it's anything heavier than hydrogen and helium. So this is usually iron compounded with some ices. So this is really important because in the core accretion scenario, all these planetary seeds form more efficiently beyond 2 AU, 2 astronomical units, so 2 times the Earth-Sun distance. And the reason for this is because here's what we call the water ice line. So basically, all the material beyond this, it's so cold here that you can actually form ices on top of these big balls of rock and iron. And then these stick together easily. So you can form big pieces of rock, like, Earth-sized or beyond that. So eventually, you go on, you keep forming these metal-rich seeds, they get attached to one another, and eventually you get to form what we call the core of these giant planets. And once you reach above 10 masses of the Earth, you actually start to go through a runaway gas accretion process in which this core just starts accreting gas like crazy, and it reaches, hundreds of times of Earth masses in terms of gas and a little bit of solids as well. So once that happens, and then the disk dissipates by mechanisms that I'm not going to talk about today, you finally have your planet, the giant planet, which has a rock ice core and then a hydrogen helium envelope accreted from protoplanetary disk with some pollution from solids. So actually, this idea that as I put here below was set about like 20 to 30 years ago. This idea actually predicts what you're seeing here. So core accretion predicts that the metallicity of the planets goes as about 1 over the mass of the planet. So the more massive the planet is, the more similar to the stellar abundances the planet gets. So the planetary envelope gets. And this is exactly what you see here. So Jupiter, which is the most massive planet, it has less enrichment in terms of metals than Uranus and Neptune over here, which have a lower mass. So we're actually starting to see this for exoplanets. So there's ways in which you can actually do the same, or not the same, but similar atmospheric characterization on exoplanets out there that I'm going to tell you about in a bit. But we only have a couple handful of points here, these red points and this blue point here. So here's the solar system trend that I just told you about, that it goes as the mass of the planets. So this is the metallicity of the host of the planet with respect to the host star. So you see this trend that, with the data set, with the data that we have for exoplanets, we cannot actually tell that they're following this trend or not. But we are trying to do this, and I'm going to pitch to you how this might change in the future. So as of today, we know more than about 4,000 confirmed exoplanets, and most of them have been discovered by Kepler using a very nice technique, which is called the transiting method. So this actually explains why I talked about transiting exoplanets at the beginning. So what we do to discover these planets is to follow the light of their stars, and whenever the planet passes in front of the star, you see a decrement in the light of the combined light of the star and the planet. So you see that the planet transits in front of it, and when you see this periodically, then you might assume you have a planet. So this gives us information about the size of the planet. So the bigger the planet, the deeper the transit that we observe in what we call the light curve here. So that gives us information about the period and the radius. So once you actually plot all of them, you plot the radius of the all known exoplanets and the periods of all known exoplanets, you can actually start seeing some populations in the data. I have to warn you, though, that most of the populations that you see here are observational biases, except for one, and I'm going to go to that as well. So the populations that I want you to look at here are these three ones, which are the ones that I'm going to touch on today. So this one, the population of hot Jupiters, large planetary radii, about 1 Jupiter radii, and about 1 day periods or a couple day periods, are the ones that we call the hot Jupiters. So these are giant planets that are really close to their stars, and therefore they're really hot. Therefore, they're named hot Jupiters. And then there's these other two populations. So this population over here are the mini Neptunes, super Earths, and Earths, which were revealed mainly by Kepler, actually, which host all these interesting, like what the press usually calls, the Earth-like worlds and stuff like that. I'm going to touch on them in a little bit. And here we have a very, not well-populated set of planets, which are these warm and cold giants, which resemble more or less, or are the warmer counterparts of our giant planets in our solar system. So the reality is that although today there are more than 4,000 confirmed exoplanets, only 300 of them have actually, are precisely characterized, they have mass and precise masses and radii. And as you can see, most of those planets that have mass and radii are in this hot Jupiter part here, just because they're easy to get, they're short periods, they're giants, so all our techniques are biased. The characterization techniques that we have are biased towards detecting and characterizing these more easily than the other ones. So there's a need to characterize these mini Neptunes and super Earths, and also these warm and cold giants that we don't see much about them around here. So this is what I'm going to talk about in this talk. So what are our efforts, and why do we care about characterizing this warm population of both giant planets and these mini Neptunes? Thank you for that.
Nothing, mother.
Systems with tests. So I'm going to pitch you about a new mission, a new space-based mission. Can you help out, Francisco?
Yeah, give me a second. I don't know what's going on. I know what's going on, but... So,
that's fine, no worries.
Si los muteo a todos... A ver, voy a mutear. Lo muteé y inmediatamente se desmuteó esa persona.
Tienes que echarlo.
Pero échalo.
Hay que echarlo.
Échalo.
Pero no sé quién es.
No.
¿Alguien sabe quién es?
Okay. I can continue, and then you can figure out who it is. So if everyone can mute themselves, please. That's okay.
Yes.
So what I'm going to pitch you is discoveries that we're making with a new space-based mission led by MIT and funded by NASA, which is TESS. This is most likely you've heard of it, is the Transiting Exoplanet Survey Satellite. So this is a satellite which is actually looking for these transiting exoplanets in an all-sky mission. So how this works is that TESS has these 4 cameras with which you get these transit light curves that I was telling you about. And then it goes through sections of the sky each year. So the first year it went through the southern hemisphere. You're seeing this in this observational setup that you're seeing here. And this year it's going through the northern hemisphere. So in order to pan out a huge survey all sky for transiting exoplanets. So for comparison, here's what Kepler did. So I missed a portion of the story for Kepler. It failed at some point. So it went to these ecliptic points here. But TESS is just something else. It's all sky. It's actually going to unveil a ton of exoplanets. And the most important thing is that the problem with Kepler was that most of the stars with Kepler, you couldn't get past the radii and their periods. That's because to estimate their masses, for example, you have to go to ground-based telescopes. And for those ones, you need very bright stars from our point of view on Earth. TESS, on the other hand, it's going to get bright stars. So you can actually go to ground-based telescopes and actually get the masses for this planet and unveil their, or have a first-order guess on what they're made of. So the TESS yield, so what are the kind of planets that TESS is going to discover, is over here. So overall, I don't want you to pay attention to this difference between FFIs and 2 minute, but the overall combined TESS yield, it's over 10,000 exoplanets in total, giving us a lot of these small exoplanets and tons of these giant planets over here. So this is a 2-year all-sky mission, which was recently extended. So we're going to go into the extended period in August this year. So it's going to do a second pass through all the sectors that are already observed. So it's thousands of new characterization systems. One of the important things is that we need ground-based follow-up facilities to get a more detailed view of these exoplanets. And this is where one project in which I'm working on, together with some folks at UAI, Adolfo Ibanez, enters. So this is the WINE survey. The acronym of this survey is not that good, but the name is great, I think, because we all love wine here. And then the whole idea of this collaboration is to go after this warm giant population that I was telling you about before. So the idea is to go after these warm, cold giants over here that it's a not very well populated region. And I'm going to tell you a little bit about why. So why do we care about these warm, cold giants? So most of the discoveries, as I told you before, have been done, most of the exoplanet discoveries or precise characterization of exoplanets have been done on hot Jupiters. So these planets that are really close to their stars and therefore are really hot and have really hot atmospheres. So the pros, of course, of these planets is that they're close to the stars, so it's easier to see them, easier to characterize them because they're smaller periods, make it more easy to follow up from, for example, ground-based telescopes in detail. However, that's also the curse of these planets. And the main reason for this is, first, any orbital information from the planet. So for example, if the planet was initially eccentric, had an eccentric orbit, for example, that's lost because of the closeness of the planet to the star. So this happens through some dissipation mechanisms in which if, for example, you have an eccentric orbit and you're very close to your star, you start losing that eccentricity due to dampening with the star through tidal interactions. And then the other problem for hot Jupiters is that the radii information is also lost. So the issue here is that hot Jupiters are so close to the stars that they get inflated, actually. The actual mechanism why the radius is larger than expected from evolution models that I'm going to show you in a bit is still on a debate. But this is a problem, actually, for actually constraining the interior structure of these planets. So the good news is that warm giants don't have that problem because they're farther away from the stars. So the orbital information is preserved from their formation, and also the radius that you observe is the real radius that the planet has, and it's not an inflation through external mechanisms like, for example, irradiation from the star. So why do we care about the orbital information of these planets? So I want to pitch to you that warm giants are both cool and that they rock. So the first reason why warm giants are cool is that there's several proposed formation mechanisms for these warm giants. So remember that these planets have orbits between 10 to a couple tenths of days of orbit, up to 100 days. And therefore, one of the big questions is how these planets actually get to this small period. Because as I pitched you at the beginning, these planets, these giant planets, should form far away from their stars. I'm speaking about 2 AUs and above. So you can imagine that that's like in order of 300-day periods like our own Earth or more. So how do they get from those large distances to the small distances that I'm pitching to you right now? So one of these formation scenarios, for example, is this migration, in which you have these seeds that I told you about at the beginning through co-accretion. They just form these big giant planets, and then they either dissipation mechanisms with the disk just start making them migrate inwards. So they start losing some of the energy that puts them out here, or they can actually do this, with a companion here. So this is this migration scenario, which is in the top. There's another proposed scenario in which you have high eccentricity migration, which is the second one here, in which you form several of these giant planets, very far away from the star. And then through resonant interactions with the companions, this planet is just kicked into an eccentric orbit, and then through every periastron passage of the planet, it just starts losing and losing this energy until it migrates inwards to an eccentric orbit. So that's one of the main predictions of this high eccentricity migration scenario, is that they should have eccentric orbits, which actually it's in contrast with this migration scenario over here. And then there's a third scenario in which these planets are proposed to form in situ. There's lots of people that, there's lots of troubles with this formation scenario as well, but, it seems to reproduce some part of the population as well, in which these planets just form where you see them today. But one of the predictions of this in situ formation scenario is that you should see these failed seeds. So, remember that I told you about Earth mass companions around here in the planetary system. So if you can actually get information about the present state of the systems, you can actually trace back to what's the most likely formation scenario for these planets. So this is one of the reasons why we care about these warm giants, because it can tell us a lot about planet formation scenarios in contrast to the hot Jupiter population. The other reason that why we love these planets, it's basically because these giant planets, as I told you before, they conserve the radii. So the radii that you're observing today is actually, the formation radius for the planet. So once the planet form with a given radius, so suppose that you have a Jupiter mass giant planet that it's, it's born hot and big, but then, if you let this flow, this equation of state of the giant planet, you just let it flow, it will start losing energy naturally from, radiating it away. So as a function of time, the planet will contract. So a pure hydrogen and helium envelope, for example, have this track here that you're seeing. So this is the age in the x-axis, and you have the planetary radius in the y-axis. So you will see the planet evolve in a different way depending on what's the amount of heavy elements that this planet has on its envelope. So for example, if it's a pure hydrogen and helium envelope, it will be pretty big. But as you start adding more metals into the envelope, the planet actually contracts to a smaller planet as a function of time. So as you can see here. So if, for example, you have a 4 giga-year planet, which is about 1 Jupiter radius and a 1 Jupiter mass, then you can estimate what's the amount of heavy element enrichment in its interior. And actually, these studies have been done. So this was done by Daniel Thongri in 2016 for a handful of the warm giants that were known at the time. And you see some very interesting correlations and lots of heavy element enrichment. So you see here that these envelopes are polluted from tens of Earth masses of material, of heavy element material, up to hundreds of times of heavy element material. So this is a lot, actually. And this heavy element material actually very strongly pollutes what the composition of the envelope should be. And in 2017, actually, we proposed predictions for what the composition of those envelopes should be. So actually, this is in the x-axis is the deviation from the C2O ratio, so the carbon to oxygen atoms in the atmosphere based on this metal enrichment. And what we proposed is in this work, for example, is that depending where the planet formed, we have different predictions about what the planet composition should be in terms of the amount of carbon and oxygen in the atmosphere. Interesting part here is that the C2O ratio here, the ratio between carbon and oxygen atoms in an envelope, defines what the atmosphere should look like. So we actually made predictions here that all these planets should be water rich. All these warm giants that we're observing, if we eventually get to analyzing their atmospheres, they should have tons of water. So this should be detectable. And there's a third reason why we are super interested in these warm giants. So whenever I speak of warm giants, I'm not only speaking about Jupiter-sized, we can also go back down to the Neptune-sized. And it turns out that the Neptunes that we see in our solar system might be just one type of Neptunes in the galaxy. The composition of the atmospheres might vary by a lot in other Neptunes out there, especially for these warm ones that I'm plotting here. So this is the composition of the envelopes of these warm Neptunes. And you can see that for low C2O ratios, for example, they're mainly dominated by water. So you will have, instead of a hydrogen-helium envelope, you would have like a water-dominated world. And this is exciting because we don't see these kinds of atmosphere here. So these warm Neptunes can actually give us a whole different view of what giant planets look like in other systems. So let me give you a little taste of wine of our project. Of course, I have no means to give you actual wine. So when you go about discovering these planets with tests, you actually observe this. So you observe a light curve, basically flux as a function of time, and you can see by eye the transits here. But it's not as easy as just going to test, seeing this, and then saying, hey, I have a planet. This is much more complicated because there might be false positives. So the object that you're seeing passing in front of the star might not be even a planet. Maybe it's a low mass star. It might also be a binary star system, which is blended, whose light is blended with other stars, etc. So there are many false positive scenarios here. So what we do mainly with our project is to go to radio velocity follow-up. So we try to confirm the planet with an independent method. So what we do is to perform what we call radio velocities, or what physicists call Doppler monitoring. So you basically try to watch the dance of the star as it's imprinted by the planet going around of it. And then this imprints some spectral features to change as a function of time. And what we measure then is the radio velocity, the radio velocity of the star with respect to us at Earth. And if we see that this period matches the period in the planet that we see in tests, then that's it. You have, a planet. So with this method, we have discovered a wide range of planetary systems. I just want to highlight two in this project. One by Andres Jordan, which is in the audience, in which the radio velocity monitoring here, you can actually see how the radio velocity varies according to the period of what we saw in the transit. And this actually allowed us to get details about the eccentricity of the system. So this shape here, which is like a zigzag, like a seesaw pattern, it's actually an evident pattern for our trained eyes of eccentricity. So we are and this also has like a long-term trend here that might be another long-term sinusoidal signal from, for example, an exoplanet. So this might be consistent with this high eccentricity migration scenario, in which this planet, which is in an orbit of around 10 days, you can actually see that it has an eccentric orbit and maybe some external companions that might have triggered its migration to the position we see it today. I wanted to also tell a little bit about extra stuff that you can do with this transiting system. So for example, here's a planet that it's in preparation, in which we actually see that transits do not happen at periodic intervals, but they have slight variations, which we believe are made by external companions as well. So this might be, so we're pretty confident to this point that this is actually a multi-planet system as well that was discovered by Wine. So warm giants are interesting, and for sure they can constrain a lot of planet formation scenarios, but I'm also interested on the discovery of planets, of small planets around small stars. This is an interest that was just driven in the past few years. And the reason for doing this, why this is exciting, is because of the following. So first, cool stars cooler stars are usually, their habitable zones, for example, are usually closer to the star because they're just cooler. So here you have a comparison between the habitable zones of hotter stars, sun-like stars like ours, and then cooler stars, M dwarfs, we call them, but down here. And you can see how the habitable zone, this green part here, which is the region in which, if you had an atmosphere like the Earth, you could expect water in the planet. This region shrinks as the temperature of the planet decreases. So obviously you have to be closer to the star to feel the same irradiation that you feel here at Earth. So this makes it easier, for example, to find habitable worlds around M dwarfs. So you don't have to wait, 300 days like for sun-like stars to see a transiting planet like this, like the Earth. For these cooler stars, the habitable zones are about 40 to 30 days, depending on the mass of the star. So it's way easier to follow up. And the other interesting thing about small planets, it's not just about the habitable zones, but it's also about studying the most common planets in the galaxy. So one of the things that Kepler taught us is that these super Earths to Neptune, so here's the size in the x-axis, in a graphical sense. These super Earths to Neptune sized are actually the most abundant planets in our galaxy. So that's one of the main conclusions that Kepler got out of its survey. One of the interesting things that just was discovered recently is that once you go to this, you do a closer, finer look at the size distribution around super Earths and Neptunes, you actually see a bimodal distribution on the planetary radii. So this is the so-called, we call this region here in the middle, the radius gap. So there appears to be a gap in the planet, so small planets come in two sizes, as it says here, in which we believe that these larger planets, about 2 to 3 Earth radii, are more akin to Neptune, so they're miniature versions of Neptune. And then these smaller planets around here are like the big giant versions of our own Earth. So there's the so-called super Earths or rocky Earths. So this was discovered mainly for sun-like stars, so FJK for the folks that know this stellar classification scheme, but not so much for these smaller, low-mass, cooler stars. And one of the main hypotheses of why this radius gap actually happens, which, by the way, this was predicted before it was observed. So the prediction was made by some folks that do some photoevaporation models. So the idea is that basically planets that are here in this rocky version of this rocky distribution of the radius gap, these planets around here are planets that actually lost their atmospheres to photoevaporation, so X-UV radiation that just blasted away the atmospheres of these planets. And these other ones above here, they just survived. So one of these two reasons, habitable worlds and the radius gap is one of the main drivers that led us to start a test follow-up effort as well within the Carmenes consortium, which is a big consortium built around this Carmenes, which is a spectrograph which is in Colorado in the northern hemisphere, and between Enrique Payet from the Instituto de Astrofísica de Canarias and myself, we're leading this effort of Carmenes test follow-up. So we have 50 nights of research reserved for this project, and we have been making a lot of progress on this. So the first, I want to pitch you three recent results that we put with this. So the first result was led by Rafael Luque, in which we discovered 3 planets around the very close by system GJ357. So we astronomers have this problem with defining distances. So for us, close by is 30 light years. That might sound a little bit dull for some of you folks, but bear with me here. So this system is composed of actually one planet that transits, so it was observed to transit with TESS. You see here the transits in the TESS photometry. And then through this precise rate of velocity follow-up that we're doing with the Carmenes spectrograph, we actually were able to extract that there were 2 extra signals, most likely planetary, and one of them is actually in the habitable zone of its star. So this made a little bit of press because of this planet in the habitable zone. But for those of you that are planning vacations to these planets, don't do it. Basically because this planet that's in the habitable zone is most likely a giant planet. So you will be very disappointed with the quality of air to be breathed in this planet. The next two planets that I want to pitch really quickly are a couple of planets that were led by a grad student here, Paz Bloom, which it's a planet exactly in this radius gap that I was telling you about, that it's not very well defined for these low mass stars. And this paper by Gregor Nowak, in which we found two planets on the same star, where the two planets are in exactly the opposite sides of this radius gap. So how they form, it's a total, a very interesting thing to investigate further. So here in the left panel, you can see where this planet is located. So here's the radiation level of the planet for this planet in the radius gap, and here's the radius in the y-axis, and you can see that the planet just falls exactly in this gap in radius that I was telling you about before. And for the planets in this paper by Gregor Nowak, you see that planet B is here to the left side of the gap, and this planet C here is to the right side of the gap. So of course, the main explanation for these planets in Nowak's paper is that this planet is just farther away. So this actually constrains, pretty well how this mechanism should work for low mass stars, which I think it's very exciting. I want to use the last about 15 minutes of this talk to talk to you a little bit about how do we go further from here. So I told you about discovering planets both around low mass stars, small planets around low mass stars, and these warm, cool giants in all spectral types. But this is talking you about, I have talked to you about so far, just about orbital properties, mass, and radius. So the question is, can we go beyond that? Can we actually study the interiors of these planets through, say, atmospheric characterization? So this is the second topic that I want to touch on in the last 15 minutes, in which is how do we do exoplanet atmospheres and how do we characterize these planets? So the main takeaway that I want you to take from this talk in terms of exoplanet atmospheres is that basically most of the work that we can do for exoplanet atmospheres can be done, like 99% of the planets that I just talked to you about can be done with transiting planets. So when the planet transits, part of the light of the star passes through the atmosphere of the planet, and then you can actually extract that small signature that the light passing through the atmosphere leaves on the light that we receive at Earth. You can extract that information and study it here at Earth. So the way in which we do this actually is through measuring the transit light curve in different wavelengths. So the main idea is that different opacity sources in the atmosphere will make the planet to appear bigger or smaller at different wavelengths. So for example, if water that really likes to absorb at around 2.3 microns, it's present in the atmosphere, then water will absorb that part of the light here, and therefore the planet will appear bigger than at other wavelengths. And therefore this measurement of the radius is a function of wavelength, or which is the same thing, the transit depth, so how deep the transit is, as a function of wavelength, give us information about the actual atmospheric makeup of the planet. So the whole idea is to form what we call a transmission spectrum, which is what you're seeing here. So it's basically the planet radius or the transit depth as a function of wavelength. So wherever there's an absorption feature, you'll see a peak in these figures, which it's typically in contrast with usual spectroscopy, in which you see absorptions when you have absorptions. In this case, you see peaks in the transmission spectrum because the planet appears bigger due to the absorption of the planet. Actually, I think, I can't remember who in the literature, but at some point they proposed that this should not be transmission spectroscopy because you're actually studying the light that it's not transmitted. So it should be like non-transmission spectroscopy, but that's too complicated for us. So we just kept ahead with this one. So this is the idea. This is the dream. The dream is to actually get the transit depth as a function of wavelength in a wide wavelength range, because that allows us to get a lot of details about the atmosphere. The reality, however, is that this, doing this with the instruments that we have at hand, it's extremely difficult. So you have systematic noise, basically because you have instruments that are not made for this kind of measurements. So these precise measurements of this transit light curves as a function of wavelength. You have stellar activity, which also poses tons of troubles in this. And you have some other stellar effects like limb darkening that a ton of people have also studied. So basically, doing this kind of work, which we call transmission spectroscopy, and every kind of transit spectroscopy you can think of, is basically at the intersection of all these troubles. So it's a tough job. That's what I want to put across. Even if you solve all these problems that I'm putting here, there are some degeneracies in the models themselves. One of the easiest ways to look at this, I think, is with this diagram, this beautiful diagram that was put by NASA at some point, in which, because you're trying to look for the non-transmitted light, there can be some important degeneracies in what you see in the atmosphere. So for example, here, in the first case, in the top panel, you see the ideal case. So the ideal case is that the light just goes through, it interacts with the atmosphere, and then you extract that information here at Earth. However, it might happen that the planet, the planet, it's either its gravity is so large, or the mean molecular weight is so large that the atmosphere is very, very close to the star, and therefore, the starlight doesn't interact that much with the planet, and therefore you don't see much of a variation as a function of wavelength. Or you can actually have as well clouds, so gray opacity sources in the atmosphere that actually dampen any feature that you might want to extract here. So this high mean molecular weight case and this cloudy case are actually degenerate, because with both of them, you don't see any or very small signatures as a function of wavelength. So this was posted in this very nice paper by Mike Line and Vivian Parmentier back in 2016. So here you have some real data points taken with HST, which has been the Hubble Space Telescope, which has been the main workhorse for this kind of studies. And you see here how they are targeting the water feature around 1.4 microns. And you see 3 different models, and all of them are completely degenerate. So there's no way of telling apart if this atmosphere, for example, has a high mean molecular weight with no clouds, which was this medium case that I was showing you here, or if it has a low mean molecular weight, but it has a global gray opacity source like this bottom case here, down here. However, there's a way through. The way through is through the optical. So in the optical range, it turns out that the properties of clouds, hazes, or any kind of particulate that is present in the atmosphere should give rise to some features, and you can actually use the optical to constrain those features. And this is why we have been super interested, along with several colleagues that are present in the talk here, to actually performing studies in the optical to complement these infrared observations. So we have actually been hard at work trying to find telescopes and instruments in both the southern and northern hemisphere to try to do this kind of work in order to perform transmission spectroscopy in the optical. So one of these instruments is the Magellan-Bade telescope, which is in Las Campanas Observatory. This is a beautiful take by Yuri Beletsky of the observatory, in which you can actually do this kind of work. And we've also been working a lot with some northern hemisphere giant telescopes. So in this case, the LBT, the Large Binocular Telescopes, it's composed of 2 8.4 mirrors with which you can get data simultaneously. And I wanted to show you briefly some results from both of these projects. So the first one I'm going to touch on is this northern hemisphere effort that we've been pulling. So the effort, it's actually really important because I remember my first ever observing run to do this kind of work, transmission spectroscopy. I was actually, expecting these beautiful light curves that I showed you at the beginning, which, they're textbook examples in which you see this transit depth, from the actual light curve. And then I was dismayed, I remember, when I actually got the data set. So this is the real data set. This is the real deal. The real deal is that you have an atmosphere here at Earth, and this poses a lot of issues. So here, if you have a good eye, you can actually see kind of the transit here, but it's pretty tough to tell because there's lots of systematics going around. So the main reason, because why we see these strong systematics here, has to do in how we do this in terms of data. So what we do is that we take spectra as a function of time. So we take every 1 minute, we take one spectrum of this star, and then comparison stars to actually mitigate the effect of the atmosphere. But even there, we see some features going around in the instruments. So the instruments are, again, not made for this kind of variations. So for example, the spectral trace, so the position of this spectra here that you're seeing here actually varies as a function of time. So the trace position varies by a lot, and this actually imposes this systematic noise that you see in the light curve. However, I think we have made a very good job in a statistical sense to actually understand what's going on, or at least marginalize over the possible sources of systematics, so you can actually model them together with the transit model, as you're seeing here, and actually have like a detrended light curve. So here you have this textbook example of the light curve, which is beautiful. So this is basically what takes most of our time, understanding the systematics and data. But once you do it, then you have these beautiful wavelength-dependent light curves that I'm showing here for the case of the Northern Hemisphere example that I was telling you. In this case, this is a transmission spectrum of HAT-P12b, which was actually shown to be flat, so there's no variation of wavelength, of the radius as a function of wavelength. So this is what I'm showing here. So this might not show too exciting, but for us it was really exciting, because what you're seeing here in blue is the ground-based data that I just showed you, which agrees beautifully with the HST data, with the Hubble Space Telescope data, which basically means that now we have an instrument that can do this kind of work from the ground with space-based precision. So this is beautiful for us, because now we have an instrument with which we can complement this infrared data that I was telling you about without the hassle of going behind Hubble Space Telescope, the Hubble Space Telescope, which it's a beautiful instrument, but the observability sometimes is not the best, and it's a really demanded telescope as well. So the LVD, yes.
What about the last point there?
Well, I'll play my big error bars card. So yeah, I think so the big point is kind of off, but it's 2 sigma, I think. So I think for our purposes, this is fine, I think.
Okay.
So this is from the Northern Hemisphere. I wanted to pitch the Southern Hemisphere for 2 reasons. First, because this is a huge multi-institutional effort that our PIs, so Daniel Abay, Andres Jordan, present in the audience, and Mercedes Lopez Morales have been putting for years, which is a project in which we, as I told you before, we are using the Magellan IMAX instrument, in which we're following actually a sample of planets, around 20 exoplanets in the optical, to complement near-infrared observations. This also has a story which is deep to my, close to my heart, because my whole PhD thesis was based on making this work, basically. And then 2 weeks before my PhD defense, there was a paper in Nature published on the exact same target that I was analyzing, but with a completely different conclusion. So here's the figure from Elyar Seragati in 2017, the Nature paper I was telling you about, that shows like tons of features. So you see like a decrease here as a function of wavelength in the transit depth, and then a little increase here, and then some features here that they claimed was TiO, so titanium oxide in an exoplanet atmosphere, which is, titanium oxide is typically seen in spots in the sun. You wouldn't expect, a layperson wouldn't expect them in the atmosphere of an exoplanet. But they saw that in their data. However, in our data, we saw none of that. So our data is composed of actually 6 observations. It's a pretty precise one. We're pretty certain of what we're observing in this case. And the precision we get is beautiful. So we see a beautifully flat transmission spectrum, which is in contrast with what the other paper studied. So we're comparing here this figure here between the 2 data sets, and you can see that this slope, we don't see it in our data, which is the white points here. These TiO features, not much. And also our data is consistent with some HST data. So it's it's still a debate in the literature, which I think it's an interesting one to know why this is. I have some possibilities, and we have some possibilities in our paper, which was published last year, that I can tell you about if you ask in the questions. But we have a very comprehensive view of this exoplanet in particular. So I didn't even tell you which exoplanet it was, because it's not extremely important. This particular talk, this is was 19b. And this flat transmission spectrum actually points to clouds in the atmosphere. So it actually puts a constraint on what this water feature that you're seeing here in the infrared actually means. I want to use the last couple minutes now that I show you that we can do this, from space, from the ground, on what the future is. So the future in my mind is related to future, current space telescopes that are extending their missions and future space telescopes that are going to be launched. And when I think of the future in terms of exoplanet and exoplanet atmospheres, I always come back, and I'm pretty sure this is the same with my fellow astronomers here, I always think about the James Webb Space Telescope. So the James Webb is launch date is next year. It's expected to be a revolution in terms of for many areas of astronomy, but for exoplanet atmospheres as well. So this is a 6.4 diameter telescope. It's like the size of a tennis court in total. And it's gonna orbit on a pretty weird orbit to most people. This is gonna be at 1.5 million kilometers from the Earth, and it's gonna be orbiting in the L2 point with respect to the Earth-Sun frame of reference. And it's gonna be always pointing away of the sun, so this is why this sun shield here is put in the telescope. So the big advantage of this telescope, it's not only its larger diameter, but also its wider spectral range that it will have. So HST, the Hubble Space Telescope, in the infrared, which is our main workhorse for infrared detections, can only target around this range, which is around 1.4 microns and a very small wavelength range. But GLUST can go all the way from 0.8 microns up to 5 microns and even beyond with some other instruments. So here's the difference between what the constraints you can get, for example, on the C2O ratio, which I spoke in the beginning, and the metallicity of the planet between HST and GLUST. So HST is this red one, so you have a wide parameter space, so basically no constraint at all. But once you have GLUST, you'll have very tightly constrained CO ratio and metallicity, which is, again, it's going to change paradigms of how planets form, what can we learn about the atmospheres of these planets to a totally different level. Now, this is not the only thing that it's going to do. It's also going to allow us to go to systems that we were not thinking about characterizing with current instruments, like these warm giants that I was telling you before. So James Webb actually has the power to transform or advance our knowledge of these warm giants as well. So here's the precision of the GLUST will get in a warm giant. So with HST, you see nothing in this data set for this planet, for example. And then these ground-based observations that I just told you about are going to be a huge, huge complement to GLUST. So one of the other things that GLUST is going to also be able to do is to try to detect effects that we were omitting, for example. So one of the effects that I have omitted in my whole talk in terms of exoplanet atmosphere is that I have been assuming that the planet terminator region, which is what we see during transit in this transit spectroscopy technique, it's symmetric in the whole planet. And this might not be the case. So for example, it might be that due to some circulation patterns in the planet, one side is cloudy and the other is not. There's some cloud patterns that we can actually try to extract. And actually, GLUST will be able to do this. So it will be able to tell us the spectrum of both sides of the planet with its very precise measurements. So this is work that Catherine Jones and I, a student that is now starting at the University of Bern, we've been doing, in which we're trying to perform a very simple extension that the usual transit model, in which instead of having a circular model, you have like a semicircle mimicking the two hemispheres of the planet that you see during transit. It's actually on a package. So if you want to model it yourself, you can go to Google, search for it. It's called Catwoman. The story behind why it's called Catwoman can explain later. And then the main effect is that this is going to allow us to see very, very gentle and small deviations in the light curves that, again, GLUST should be able to detect as a function of wavelength, which is amazing. So we just want to end the talk with some take-home points. So the first one is that there's a need for more characterizable systems, exoplanets. So the ones that have mass and radius, as I showed you at the beginning, are not many. and also the ones that we can actually characterize their atmospheres is not a large number. So there's a need that I think TESS, and this is my second point, it's been an excellent job at characterizing these exoplanets, at discovering them, and then we, as follow-up teams, were actually getting precise measurements for them. The third point that I want you to take out from this is that there's excellent complements to space-based observations, both present and future, in the ground. We've been doing a lot of work here. We're not the only team doing this, by the way, so I just noted the ones that we're doing, but there's different teams trying to get precise measurements from the ground for exoplanet atmospheres, and I think we're doing the job. Finally, GLGST will be just revolutionary, this James Webb Space Telescope, for transit spectroscopy studies. So it will be the first instrument for which I think will be prepared to examine the atmospheres of distant worlds. So that's it. Thank you very much.
All right, Nestor, thank you very much for the talk. Let's start with the questions. Are there any questions?
Remember, you have to unmute yourselves.
Yes. Does anybody have a question? You're all mute.
Néstor.
Rafael.
So what will be the complement that the future giant telescopes that will be installed in Chile will make on this type of science? So the complement between the GMT, for example, and the Webb.
Yeah, thanks for that question, Rafa. So yeah, so the detail in which the detail of the talk that I just gave in terms of the exoplanet characterization is that the kind of pressures that you prove, or the portions of the atmospheres that you probe in the kind of exoplanet spectra that I just showed you is going to be different to what these giant telescopes are going to actually probe. So this is the difference that we usually talk about within the exoplanet community between the low resolution spectroscopy and high resolution spectroscopy. So the whole deal, for example, with GWST is that first, it's going to be mainly in the infrared, and the resolution that you see here, I mean, for most spectroscopists, the resolution that you're seeing here is not large. This is a very low resolution. So this water feature, if you look at it in detail, it has much more features going around that you cannot see because of the low wavelength resolution of GWST in this case. So the advantage of going to higher resolutions is that you can actually probe pressures in the atmosphere which are higher up in the atmosphere, which you basically lose in this kind of measurements that you're seeing here at lower resolutions. They will be totally complementary in that sense, because only with both you will get like a complete picture in a whole range of pressures about what is really going on in the atmosphere. And this is, I think, is the power of the future giant telescopes, that they can not only be a complement, but they can sometimes tell things that GLGST will not be able to do. And second, the wavelength ranges that ground-based telescopes, these ground-based telescopes are going to touch on, are going to be complementary to the ones that you're seeing here.
More questions?
Yeah, I have a question. Nestor, the JWST, it's going to last for about 6 years, right?
Yeah, 5.
So how many planets will we be able to observe? Because, you know, each planet is expensive to observe, and how much are we going to get done?
Yeah, that's a very good question, and for which I think no one really has an answer. In the sense, I mean, if you take the order of magnitude calculation that perhaps based on what was selected as an early release science. So the idea, what I'm talking about here is that there was a director call for the James Webb Space Telescope time for early release science, in which some certain scientific areas were selected to do some studies, guarantee studies with James Webb before the nominal call for proposals, which is ongoing right now. And with this, like around 20% of the time was dedicated to exoplanets. So if we assume that that's gonna go on for the 5 years of operations of GWST, that's 60 days of observation per year. So times 5, so that's like 300 hours. And if you take, a 7-hour or 10-hour observation, that's in the order of 30 planets. So it's not going to be a lot, for sure. It's not going to be like a ton of planets, and we have to go forward with this mission. So I hope this lasts more than 5 years, because then you can do more. But if it doesn't, then it's on us to actually go behind these systems with future instruments. And this is where these giant telescopes can actually pan out very well, because those ones do not have, a 5-year timeline mission. So yeah, that's also the advantage of the ground-based instrumentation. But also, there's other instruments in the horizon, like Ariel, which is thought to launch in 2028, which is going to do, big surveys of exoplanet atmospheres. But I think the power that GWST is going to give us is quite unique, though. A 6.4 diameter with this kind of instruments that you see here, it's just kind of unique.
Thanks.
Sorry, I never heard that James Webb Telescope was going to be only 5 years. Was only be 5 years operating. Is that because it's too big? They
can't recall the exact.
Sorry.
Can't recall the exact reasons. But it's
because Hubble was 20. Well, but it was much more smaller. But yeah.
Yeah, it was smaller. It was in a different orbit. So HST.
The Hubble Space Telescope is on a low Earth orbit, Pia, so you can go service it. It's very expensive, but you can go fix it.
That's true. This is Lagrange 2?
Yeah. So it's not.
Okay.
I mean, by contract, it's not supposed to be serviced. It's very far away, 1.45 million kilometers.
That's true. Yeah. I forgot about that.
You cannot.
It's going to be launched, though.
I'm not sure about that, Andres. I mean, for sure you cannot send someone, but you can send something.
No.
Okay.
And Néstor, it's going to be launched, right? It's confirmed, and no one is changing that.
As a Space Telescope Science Institute employee, my official answer to that question is March 2021.
Okay. Okay.
I have a question, Néstor. What are your thoughts about investigating Earth-like planets within the habitable zones of their stars with these techniques? Is there any chance to catch something, to get something out of these planets?
Yeah, in my view, that's going to be a marathon more than a sprint. Meaning, most likely you won't get it done with GLGST. Like I'm 99.9% certain that's not going to be done with GLGST. With ground-based telescopes, it takes just a ton of time. Mercedes, Lopez Morales, and Florian Grodler from ESO, they have some measurements on this, like some papers about this, like in the order of 30 to 50 nights of observation with the giant telescopes in total to get, one oxygen detection. And that's, detecting oxygen only, it's not enough for biosignature tracking. So I think we really have to think beyond what we're thinking right now. Louvois and the HAVEX observatories that are planning to do this with direct imaging are starting to do that. But I think I have more faith in other instruments out there, other propositions out there, in which we basically have to start thinking outside of the box a little bit if we're gonna go beyond, getting one planet with one signature. So if we want to go, the question is, do you want to go for one and then we just put all resources for just one or a couple? Or do you want to really understand what the habitable zone of sun-like stars actually look like? And that's the question I personally am more interested in, the latter one, because it could be that the atmospheres of Earth-sized, Earth-mass planets around other stars, maybe their atmospheres are nothing like the Earth. Maybe they're all Venuses. Maybe they're all Mars-like. And that's the most pressing question that I think we should really aim for. And that's a tough one with present and already planned technology. But I think that's the way of advancing. So you go step by step. I think the steps that are being taken right now are fair, are good, but we have to keep, breaking those limits in order to get to those. So that's a very, very harsh topic, I think, technologically speaking.
More questions, folks?
So, Nestor, I missed your answer to my question because I lost the connection, but it doesn't matter. I can answer.
No.
But
no is the answer.
Maybe related question, maybe you already answered this in the last question is, so the James Webb won't have a high resolution spectrograph to study atmosphere of planets, right? Is that due to technical limitations, or is a scientifically based decision?
I think it's a little bit of both. So I think that the highest resolution that I can think right now, it's MRS, so the medium resolution spectrograph on board of MIRI, which is a couple hundred, tens of hundreds, if I can recall correctly. And even there, it's not like the kind of instruments that we are used to here in Earth. So I think it's a little bit of both. First, of the number of instruments that you want to put on space and the science that you want to do, and also a technical challenge. So as you know more than probably all of us, putting like a stabilized spectrograph anywhere, it's extremely tough. And then putting it in space and maintaining that stabilization as a function of time is just extremely harsh.
Yes, okay, thank you.
More questions?
Also, by the way, MRS, it's not 10, it's like 3,500. So it's the medium resolution, but the nice thing is that's gonna go longward of 5 microns. So it's gonna go all the way to, 10, 15, 30 microns.